Now, let us take a piece of magnet and let us call it as north pole, and somewhere there on the left side you will see the south pole for that piece of magnet. Let us take another piece of magnet and let me give it some space. Let us take another piece of magnet and place it at some distance in line with the north pole, but the south pole facing the north pole, and this has a north pole also, of course, because no magnetic element can be with an isolated pole. So, it has its own north and south poles, but we are interested in this, that is up to here. Now, here if you see the magnetic lines of force, this is at quite some distance, it is not quite near it because this is much further than the distances that we are indicating here. So, that this north pole does not have much interaction with the field lines which are occurring here. Okay. Now, if we take the field lines, there is a flux from the north to the south. It starts going from north to the south. It is quite strong north to south, but in this direction, the field in an orthogonal direction is 0. Now, in an arbitrary direction at an angle, the field is going to exist, but it is going to keep decreasing. Let us say we take the we draw a circle. Let me draw a circle. As shown like that. So, we have a circle here, and if one travels along the periphery of the circle, at this point the field is strong and positive. At a point here, the field this is at a point which is orthogonal to this north-south axis, and the field there is 0 in that direction. At any other direction, let us say at when we are at a point here, then the field will be a bit reduced. Would be a bit reduced compared to the position on this, because it is not directly in line. And then if we take a point somewhere here, the field will still further be reduced, and still further if we take a point somewhere here, the field is positive still, but still further reduced, and so on till it becomes 0 at this point. And then further, if I consider a point on the circle circumference here, in that direction the field starts becoming negative, because if we consider a point here, with respect to that point, the field is going to the point, not away from the point, and therefore at corresponding to this point the field direction is negative and it is shown by this negative arrow. And as this point starts in this circumference, as this point starts traveling like this would be going in this fashion with increasing field gradually till it becomes maximum and negative at this point. So, you see that there is the field goes in this fashion, in a sinusoidal fashion here. Now, with a maximum when it is at the north pole, negative maximum when the position is at, when a point is at the south pole, 0 at both the orthogonal points. So, when the point starts moving at this point, we see again the mirror image of this, and then when this starts moving again towards the orthogonal axis, you will see the field decreasing. Field starts decreasing until it is 0 at the orthogonal axis, and as the point further continues, it becomes positive, that is, this is the positive direction, this is 0, this is the positive direction. So, field again changes direction, and you will see that radially there is different amplitudes till it reaches the positive maximum when the point has again reached this point. So, you see that if there is a point which is situated on the circumference of the circle starting from the north pole, the point located near the north pole, if the field is moving away from the point, it is, we are putting it on the right side of this axis, and the field is on the south pole, the field is entering the point, and then that is considered as negative. So, a point which moves around the circumference like that starts with a field which is positive and then keeps decreasing as the point is moving along the axis there, decreasing in this sense till it becomes 0, and then it goes negative in this portion of the segment, keeps going so on till the field is negative maximum, till it is negative maximum as shown here at the nearest to the south pole point. And as the point traverses along the circumference towards again the orthogonal axis, this traverses, the amplitude starts reducing further again till it becomes 0 when it is at the, when the point is at the orthogonal point, and then this goes again in this direction, changes direction and becomes positive max when the field again goes to this point. So, this is how the field would look like when a point traverses on the circumference as shown here when we place north and south poles. So, this would be the 0 of the field phasor, the field vectors. Okay. So, this would be the picture of the field vector. field vector spatial picture. Okay. Now, let us have a north pole and a south pole, and let me have a conductor with some as such there is no such current in the conductor. Let us say that there is a field which is existing from north to south in this direction. Now, this is a conductor. Now, this conductor, if it is stationary, the field that is linking the conductor is also constant. There is no d phi by dt. So, as there is no d phi by dt, there is no induced voltage in the conductor, and therefore, there is no current flow in the conductor. If the field is changing, if the amplitude of the flux here, amplitude of the flux phi here is changing, then there is a d phi by dt, and this results in an induced EMF in the conductor, which will result in a current to flow through the conductor in a specific direction. So, therefore, what is essential is a changing field for current, for a voltage to be induced in the conductor and thereby a current to flow in the conductor. Now, there are two ways in which to produce a changing field as far as the conductor is concerned. Let us say the conductor is fixed at a point. Now, the flux phi here can change with respect to time. Flux is a function of time. Then amplitude here changes, and therefore, d phi by dt is finite, not 0, which will induce a voltage across the conductor and thereby a current to flow. The other way is to have flux fixed. Flux is fixed, the flux amplitude is fixed. You have a permanent magnets north and south pole, and therefore, the distance between them is also fixed, and therefore, the flux phi is fixed. Under such condition, the only way that you can have a change in flux is if the conductor moves. If the conductor moves, let us say to this position, then the flux at that position, which is at a radial angle, is going to be lesser, and if it moves still further, the flux is going to be lesser. If it is at orthogonal axis, the flux there is going to be 0, and let us say it continues to move. So, the flux amplitude that is going to cut the conductor is going to keep changing as the conductor moves along the circle. So, that is the movement of the conductor is going to give you the d phi by dt, which is going to induce the voltage and thereby a current to flow. So, this is the other method in which induced EMF can also be produced in the conductor. So, in the case of DC machines, the flux here is kept constant by means of the fixed permanent magnets, let us say, or something that produce constant flux, and thereby the only way that you can produce an induced EMF in this conductor is by moving the conductor along the periphery, which means that this conductor is going to see varying amplitudes of the flux at different amplitudes at different points on the circumference of the circle, and therefore, a d phi by dt, and therefore, a induced EMF, and therefore, a current to flow through the conductor. This comes by from the Faraday's laws of electromagnetism, where you know that the induced EMF which is equal to n d phi by dt. An alternative expression in terms of the conductor length can also be derived, which is, let us just modify the okay, and then we have this. Okay, so these are the magnets, and then of course there is the conductor. Okay, so this conductor is positioned like this, and then you have all the flux lines linking the north and the south poles. Now, if this conductor is having a length L, and then there is a cross section area AC, and therefore flux by AC is going to be the magnetic flux density B, and then if the conductor is moving at some speed, let us say V is the velocity in meters per second at which the conductor is moving, cutting across the flux, then the voltage E induced is also given by B, the flux density, which is a constant of course in this case, because phi is a constant, AC is a constant, L is a constant again because this is the length of the conductor, and V, which is the velocity at which this conductor is moving in meters per second, and this is what is cutting the flux, and therefore as it is moving, it is at various radial distances, angular distances from the center, and thereby the flux amplitudes are going to be varying at different positions, and that is going to cause the d phi by dt effect, the d phi by dt effect here, the meters per second, and it is going to result in a induced EMF in the conductor. So, the induced EMF in the conductor, this gives the induced EMF in the coil, which has N turns. This gives the induced EMF in the conductor, which has length L, moving at speed V meters per second. So, both are actually one and the same law, Faraday law of electromagnetism. Whereas one is with reference to the coil, the other is with reference to the conductor. So, now we start again with the north pole here, and we have a south pole here, and let me also have a circular marking which gives the periphery in which the conductor is going to rotate, is going to move about. So, let us now have a conductor which is positioned like this. So, once we have the conductor, this single conductor positioned like that, now let us see the current through the conductor as it is moving along this field here. So, as it moves, let us also take the position. Consider an imaginary, now let me draw with a different color. Consider an imaginary xy axis this is spatial, this is a spatial axis, spatial coordinate system. So, when the conductor is in this position, the flux is full max and the conductor starts rotating from here to this point, moves from here to this point. The flux at these points are gradually decreasing until it becomes 0 here. So, you have the flux which reduces becomes 0 at this point. Then from here to here, the conductor is at the south pole, the flux is at negative max, and then when it further goes, the flux keeps moving in this fashion, 0 again at this point, and then when it again moves here, the flux value is back again to its positive max. This is the 0 as far as the flux phi m is concerned. So, this is the alpha axis and the beta axis in the spatial coordinate system. Now, when the flux is at this point, we are talking of this maximum. So, therefore, you have the induced EMF E which is equal to B L V. The B is maximum at this point, the induced EMF is maximum, and therefore, the current which is going to flow through the external load is also going to be maximum. So, if we now project this on the temporal axis, let me now draw the amplitude of E, the induced EMF with respect to time. So, as it is at this point, let us call this as A. So, this point is A that we are going to begin. Okay, this is at 0, sorry, this is at peak. Let me so it is at this point, this is 0. So, this is at E max, then it rotates 90 degrees and it becomes 0 here, and then from this is point B, this is point A, this is point B corresponding to the spatial, this point C and D. So, from B to C, this is going negative. So, this starts going negative and reaches the maximum point C in the other direction, negative direction, that is here, and then from C to D it again becomes 0 in the orthogonal axis orthogonal to the alpha axis which is along the north south pole direction, and then from there this is point D, and then again D to A. This again is point A, comes back to. So, this keeps going on and on. This is for one complete cycle of rotation. You see that you get a almost sinusoidal voltage that gets induced on the conductor as the conductor is moved from A to B, B to C, C to D, and so on. Now, this gives the basis for generating some voltage from the mechanical rotation of a conductor to an electrical induced voltage.